A bed rest study is a model used to mimic weightlessness on ground. Actually, it induces the same physiological changes as weightlessness. We put the volunteers in head-down tilt position at -6 degrees, and all the activities are done in bed. Shower, eat, watching TV, leisure, everything is done in bed.
The participants in these experiments can spend up to 2 months in bed.
The bed rest studies have two aims. The first one is to study physiological changes induced by microgravity. And the second one is to design and test new countermeasures to counteract the effects of weightlessness on the body.
MEDIS is currently testing a short-arm centrifuge which could help prevent the negative effects of weightlessness during long-term space missions. The spinning motion of the machine mimics the effects of gravity. The centripetal force on the body could be a way of ensuring a blood pressure gradient and some physical stress on the bones, similar to those on Earth.
It works like a ride in an amusement park because it creates a centrifugal force that recreates the gravity along the body axis.
The idea is that astronauts would spend a short time in the machine every day to counteract the effects of weightlessness. You could call it a trip to the spin gym. Devices like these will be essential if we are to ensure the health of astronauts when we send them on long space missions. We have seen how our bodies have evolved under the pull of Earth's gravity and looked at some of the problems that need to be overcome when we spend long periods in weightlessness. But this is not the whole story.
Assuming that astronauts have plenty of oxygen to breathe, food to eat and water to drink, the next challenge they face during long space missions is less obvious: radiation.
We have evolved to live with protection from the radiation coming from the sun and from outer space. Earth protects us from this lethal radiation in two ways. Our atmosphere protects us with a layer of ozone that absorbs 97% of the sun's harmful UV radiation. Fortunately for us, UV radiation is very easily blocked. Most of it can't penetrate ordinary glass or even a thin layer of clothing. This means that in space, UV is not a problem inside the spacecraft, and the astronaut spacesuits protect them from UV when working outside.
However, there are many other different types of radiation coming from space, which can play havoc with the cells in our bodies if we receive large enough doses. This is high energy radiation, mostly composed of X-rays, gamma rays and cosmic rays.
Once again, our planet protects us from this high energy radiation. The Earth's core creates a magnetic shield called the magnetosphere. It surrounds Earth, reflecting most of the incoming charged radiation.
Doses of radiation are measured in units called sieverts. Scientists estimate that the average person on Earth naturally receives 2.5 millisieverts per year.
This level is so low that we can consider it safe. However, a 6-month stay on the space station exposes the crew to the equivalent of about 600 chest X-rays. That is why on the ISS, astronauts' radiation dosage is carefully monitored on a daily basis. A round trip to Mars would expose an astronaut to a dose of radiation that is the equivalent of their lifetime's limit, enough to give them a very high risk of developing cancer. This is clearly unacceptable, and ESA is developing technologies to reduce these risks.
To look at the long-term implications of high radiation exposure, a human-like torso called Matryoshka was fixed to the outside of the ISS in 2004. It is made of natural bone and human tissue-like material.
Continuing with mounting activities for the Matryoshka experiment.
After 1.5 years of exposure, it was brought inside the ISS to measure the radiation there. The results will be used to develop technologies to protect space travelers from radiation during long periods of time in space. We've talked about some of the physical challenges of long-term space exploration, but what about the psychological challenges?
Scientists like Dr. Oliver Angerer are studying the psychological effects of confinement and the implications for long missions in space.
You have a limited number of crew members living together in very small quarters with limited privacy. So any small factor of daily life, certain habits that people have, for example, that you would disregard in a normal terrestrial environment, simply become much more important and can lead to significant conflicts. In the worst case, of course, you can have people really developing severe psychiatric symptoms. It could be a possibility in long-duration spaceflight in the very worst case. This can really be a major danger for mission success.
In Antarctica and Russia, ESA scientists are currently researching the psychological issues that will arise on long-term space missions. In 2009, 6 volunteers will climb through the hatch of a Mars 500 spaceship mock-up and not come out for over 500 days.
Dr. Jennifer Ngo-An is leading the ESA part of the research effort.
The crew members will be locked up with 5 other crew members for a very long time. So they will have to deal with each other, they have to get along, they will have to solve problems, and especially being away from their friends and family will have an impact on the crew members. In order to make the Mars 500 program as close as possible to a real spaceflight mission to Mars, we will introduce a couple of measures that the crew member will not like. Among those are that they will have to eat the food like astronauts on the International Space Station. There will be a communication delay. In the worst case, we are looking at a 20-minute communication delay. In addition, there will be no shower in the facility, so they will have to adapt to the conditions that the program and a real spaceflight mission will have.
As we have seen, there are many challenges to long-term spaceflight. To live there, we have to find ways to supply all of our energy, air and water needs. We need systems that help us survive in very confined environments, and we need ways to guard against the effects of weightlessness, which in the long term can have serious consequences for our health. But our desire to explore has always driven innovation and adaptation, and we've come a long way. In as little as 10,000 years, we have developed technologies that have totally transformed us and the world in which we live. In the last 50 years, we have put man on the moon, and now ESA and its partners have a permanent crew of astronauts on the ISS, where we are preparing to take the next step.
We're only at the beginning of our journey. Who knows where it may lead? Will you be one of the first pioneering explorers on Mars? Or perhaps you'll be one of the many space scientists like me that will help to make it all possible.